Now that we've added functions to our armamentarium of tools, we're going to see that that gives us a lot of power in terms of thinking about computational ways of tackling problems. Functions give us, as we said, that ability to abstract, to capture a computation and then wrap it up as if it were a primitive. It gives the user the ability to treat a function like a black box. You suppress the details and you just use the contract, that specification that says, if you give me things that satisfy certain constraints, this function will give you back answers that meet particular desires. That's great. But even functions can come in different flavors, and there's some real power to thinking about different ways of tackling a computational problem. And I wanted to spend a little bit of time in this section talking about that. Let's start with what we've seen so far. We've really been using looping constructs as our way of building algorithms. And those looping constructs, things like a while loop, a for loop, lead naturally to what we would refer to as iterative algorithms. They iterate their way through the loop, going over and over the same computation with slight changes. And in particular, we can think of an iterative algorithm as capturing computation in a set of what we could call state variables. These are variables that describe the state of the computation. And those variables update or change their values on each iteration through the loop. Let's look at an example. So here's a simple little example. Imagine that we want to do multiplication, and we're going to do it just using successive addition. Our computer only comes with addition. It doesn't come with a built-in multiply. I know that's dumb, but it gives us a simple example to deal with. If we wanted to do that, to do multiplication by successive additions, then a simple way to think about it is to say, if we want to multiply a by b, we're just going to add a to itself b times. And iteratively, what does that mean? Well, iteratively, we could say the computation is going to be captured by two variables. One is the iteration number. Which time through the loop am I at? That number, let's call it I arbitrarily, is going to start off at b. And the second thing we're going to need is a state variable that captures how many additions we've already done, what the result is so far. Let's just call it result. So that's the current state of the computation. And that starts off at 0. So notice each of these state variables has an initialization. We started off somewhere. And then we think of the computation as iterating through or updating those state variables. And those update rules in this case would be that on each iteration, I, my iteration number, is going to reduce by 1. And result, the thing that's holding the computation, is going to take the current value of result, add the value of a to it, and that becomes the new value of that state variable. So these state variables have the property that if I stop the computation at any point, they tell me exactly where I am. And they have the property that not only are they initialized, but at least one of them will have a condition for telling me when I can stop. And in this case, I'll stop when that iteration count gets down to 0. I know I've done all the things I need to do. We've seen examples like that, but this idea of iteration is nicely captured. And if we put it into code, in fact, we see something that very nicely builds on that. We initialize one state variable. In this case, we're going to just use the parameter passed in as the other state variable, and it's initialized when it is passed in. And then the loop simply has updates. There's the updating of those state variables. And let me make a simple comment about this format, since we haven't used it before. That format is the same as saying, let result be bound to result plus a. And this one is saying, let b be bound to b minus 1. It's simple little shorthand for doing that kind of computation. And of course, when I'm done, I'm going to return the result. We've seen these kinds of examples before, and you can see how iteration is a nice way of thinking about it. That loop actually captures what the changes in the state variables are at each point. And if we wanted to try it, we could certainly go over here to Python. And there's my definition of itermul. And if I load it into a scheme environment, an idle environment, rather, then I can certainly say things like, give me the iterative multiplication of 3 and 5, and it does the right thing, and I can even be more fancy about it and say things like, and it does it pretty quickly. We haven't shown out the intermediate stages of the loop, but you've seen enough examples of this to realize that it is, in fact, doing that, counting down of B while accumulating the results in result and then returning the value. Great.